Okay, we will continue our discussion on asymmetrical machines. Last class we say we found out how the rotating field theory can be used for asymmetrical two phase machines. Okay. If you have two phase machine, they are what are the two phase machines are typically applied for single phase motors as well as for two phase control motors. Two phase asymmetrical windings at quadrature, auxiliary winding leading the main winding by 90 degrees, and many times and auxiliary winding having different number of turns than the main winding, normally more than the main winding turns. Next, auxiliary winding having external impedance in the form of capacitors. So, this is the actual ground situation, right. I hope all of you are clear about it, what is a two phase machine practical situation. Okay. Then that means we have already said it is for split phase winding or capacitor winding, okay, with asymmetrical two phase machine application, single phase motors. Okay. Then we have always said that in asymmetrical case it could be interturn faults, capacitor motors, and how to find the capacitor for good starting and good running, and variation capacitor for best performance. That means, what is the capacitor for starting, what is the capacitor for running in order to get the best performance. So, this is all part of the practical problems one faces in analyzing two phase machines. Okay. Then we also know that practical connection is the main winding M and auxiliary winding A, and that auxiliary winding will be leading the main winding with the same squirrel cage rotor, and the supply is connected to both the main and the auxiliary winding, okay, maybe with a switch, and you can also have some capacitors in series with the auxiliary winding, but same voltage will be there. This is a practical situation. Okay. So, the angle between them, main winding will be leading will be lagging, the angle by theta is 90 degrees, and number of turns are A versus number of turns are M, we take it as A. Okay. Then in the last class we said, then you can always write this as Vm Va will be equal to an impedance Zmm, Zma, Zam, Zaa, and multiplied by these RMS values Im and A, isn't it? This is what we said. And what is the values of these? Zmm was its leakage impedance plus Zfn plus Zbn, and Za will be Zla plus A square, A is the number of turns, A square into sigma Zfn Zbn harmonics, and Zma is A into Zfn e to the power minus jn pi by 2, Zbn e to the power plus jn pi by 2. Okay. N is the harmonic number and pi by 2 because they are displaced by 90 degrees electrically, and Zam is the same, Zam is Zma conjugate, because Zfn e to the power plus jn is a minus j is plus jn here, this will be Zbn e to the power plus jn minus jn pi by 2. Okay. This is what we had done, and with only fundamentals, that means n equal to 1, we said Zmm is Zlm plus Zf1 plus Zb1, Za is Zla plus A square Zf1 plus Zb1, okay, and Zma is A times Zf1 e to the power of minus j pi by 2, Zb1 e to the power plus j pi by 2, and Zam is minus j become plus j here, A into Zf1 e to the power j pi by 2 plus Zb1 e to the power of minus j pi by 2, and we have already defined what is our Zf1. In fact, in this case it is xm by 2 Rr by 2s, okay, j xlr by 2. Unlike the earlier in earlier we had done. It is just a matter of minor variations. Okay. Then we had to write, last time we wrote the voltage equations. Okay. What is that means we had to just Vm Va you can write down, is not it? Okay. And those equations are already there. So, that will be ZLM plus ZF1 plus ZB1 okay, into Im plus minus JA ZF1 plus JA ZB1 into Ia. Okay. Then Va is again ZLA plus A square ZF1 plus A square ZB1 into Ia plus JA ZF1 minus JA ZB1 into Im. Okay. Then what we do here is, next what do we do is we refer to main terms. So, we know that that means we say Va dash is Va by A and Ia dash is Ia into A and Za dash will be equal to Za by A square. This is how we transform this, and then we get so Va dash will be ZLA dash plus ZF1 plus ZB1 Ia dash plus J times ZF1 minus J times ZB1 into Im. So, earlier one get transformed to the main winding turns. So, we define also next is we have referred to auxiliary winding to main turns like this. So, we have Vm Va dash, we have the equations. Okay. We have already written the equations. Okay. And what is the next thing is we write VSF, VSB, ISF, ISB. So, we have defined VSF is half of Vm minus Va dash and VSB is half of Vm plus Va dash, sorry. Okay. That is what you will do. Okay. Now, ISF will be half of Im minus J Ia dash and ISB will be half of Im plus J Ia dash. So, we make this substitution and then we have we get the following, that means we get VSF will be half of ZLM Im minus J Ia dash ZLA dash plus twice ZF1 ISF. Actually, I had asked you to derive all these things, okay, and bring the assignment today, but none of you have done this, okay, which is not proper. Okay. Now, we have, so this will be okay. Now, VSB will be half of ZLM ILM Im plus J Ia dash ZLA dash plus twice time ZB1 ISB. This is what you get, VSF and VSB. Okay. Now, you can also go a reverse way and write I m and I a dash in terms of ISF ISB. So, we can easily find out I m will be ISF plus ISB and I a dash will be ISF j times ISF minus ISB. Okay, this is a reverse, right. So, we have, I mean basically we have I m I a or I m I a dash, we write it in terms of ISF ISB. Okay. Now, we do a little algebraic manipulation through this, and what we have is we will have these expressions. VSF will be ZL M ISF plus ZL A dash minus ZL M by 2 ISB plus twice ZF1 ISF. Okay. And we similarly we get an VSB will be ZL M ISF plus ZL A dash minus ZL M by 2 ISB, then no, actually this is ISF minus ISB, sorry. This will be into ISB, no, this will be ISB minus ISF plus twice ZB1 ISB. Okay. Do you remember you have done similar things earlier? Okay. So, basically what we have is VSF will be ZL M ISF plus ZD into ISF minus ISB plus twice ZF1 ISF and VSB is ZL M ISB plus ZD into ISB minus ISF plus twice ZB1 ISB. Okay. Now, from these two equations, what can you get? You have two equations and two unknowns, isn't it? Right? So, you can draw an equivalent circuit, right. So, I have a VSF and I have a VSB. So, VSF will have ZL M twice ZF1, okay, and then ZD and here you will have again ZLM twice ZB1. Okay. And where what are the currents? What are the currents? A simple circuit loop equation. It satisfies, and where ZD is half of ZL A dash minus ZL M, is not it? So, but ZL, what is ZL A dash will be auxiliary winding, resistance, leakage reactance plus any external capacitor that you connect. Okay. Now, if they are totally identical windings, what will be ZD? If main and auxiliary windings are same, symmetrical, ZD will be 0. Okay. So, this will become a short circuit. Okay. And in fact, if you want to expand, so if you expanded circuit, we will have ZLM okay. Now, this will be, let us say, R M J X L M, is not it, ZLM, that is the resistance and leakage of the main winding. Okay. Now, what will be these parameters? This is basically twice ZF1, and according to the definition which we have, twice ZF1 will be JXM, because is not it twice. So, this will be JXLR, this will be RR by S. Okay. So, this will be ISF, ISB. Now, what will be this parameter JXM? RR by 2 minus S JXLR. Okay. Because sometimes people also add some resistances here. Why? Right. Core loss corresponding to the forward flux and core loss corresponding to the backward flux. Okay, that is what they do. Right. Now, I think this will be twice ZB, is not it? I hope you understand that the factor 2 is suitably accounted for. Ultimately, it is the same parameters. And what are these parameters? What are these XLR and RR? Rotor resistance and leakage reactance refer to stator main winding turns, when the rotor is assumed to be a 2-phase. Rotor is assumed to be, please note down this, rotor is assumed to be a 2-phase system, it is not a 3-phase. If it is 3-phase, you get a different number, is not it? If it is 5-phase, you have a different number, rotor can be M-phase. Therefore, our XLR RR are defined on a 2-phase system, okay, and that is why we get these quantities. So, when you do a measurement, when you do a testing, you know what are you measuring, okay. Right. Now, what will be the current here? What will be the current here? This will be IRF. This is the rotor current due to the forward field. This is the induced rotor current due to the forward field. Okay. Similarly, this will be IRB. Okay. So, these are the rotor currents due to the backward field induced because of the forward flux. It is the flux which induces the voltages and currents in the rotor, not the MMF. Okay. Right. Now, what will be the torque? What will be torque in such a machine? We have seen torque will be equal to Tf minus Tb, is not it? So, what was Tf? Will be twice ISF square into Rf, is not it? Where no, let me tell you that this will also be equal to twice okay. This is that forward torque, because that is whatever power you are feeding to the forward field, power in the forward field is the synchronous torque. Okay. Then similarly, Tb is twice by omega s, omega s synchronous speed in mechanical radians per second. Okay. I S B square R B, R B is the resistive component of ZF in this. Okay. This will be equal to twice by omega s I R B square R R by 2 minus s. Okay. So, I want you to develop a MATLAB program in which if you are given a machine parameters for any type of capacitors. So, now you can in fact you can vary the capacitor, okay, and you find a capacitor which will give me a good starting torque, right. Good starting torque means what? Because it is Rf equal to Rb at starting, is not it. So, it will be basically ISF square minus ISB square. Good starting torque is you would like to have ISB at starting 0, is not it. Maximum starting when do you get? You must have no backward this thing at all. So, you see whether it is feasible or not, so you minimize. Okay. So, you can play with if you develop a program, you can play with these things, okay, and get the performance. So, you have a interesting software to develop. I think it is not a big deal, okay. It is a simple simulation of these expressions, okay. Okay. Now, I will take you to another practical case, 3-phase induction motor with single phase supply, right, because making a single phase motor is more involved. There are very few people who are making it and also you know it has always a backward torque problem whatever it is, and also it is more expensive. So, but 3-phase motors are available. Can you think of operating only on a single phase supply? Okay. Now, the other motivation for this is that there is one positive motivation and the negative motivation. Okay. Okay. I will say positive, first I will say positive motivation. For this thing is that people are now talking of HVDS, high voltage distribution system. See, all your distribution systems are generally low voltage. At your substation, what is the voltage? What is the voltage in your substation? 220 at your house. Substation, what is the voltage? 11, so typically you have 11 kV to 415 volts, 3 phase, okay, low voltage distribution system, and it is the low voltage distribution system which has very heavy losses because wires are small. In this case, distribution means you are not wires, because for same power you have to take thicker wires anyway. So, losses are high, and your copper is more, and since it is low voltage, tapping is easy. So, it is easy for stealing of power. Okay. Now, 3 phase is a problem because you need a 3 phase transformer. You need a 3 phase transformer, 6 winding and etc. Okay. 3 phase transformer feeding to 3 different houses, unbalanced and all these problems, etc. Now, the people are now saying, if it has been in the air, I think people are seriously thinking about it, is what is known as high voltage distribution system or SWER. It is called single wire earth return. So, you are returning through mother earth, your current, you do not have. So, all you do is, if there is a consumer, okay, you just draw one line, single wire, this is a transmission line, and through which you supply power to the consumer, okay, and earth return, okay, single wire earth return system. So, this may be, that means what you do is you almost take this, you can have a transformer which may be high voltage, low voltage, that means up to the consumer end you can take the nearest to the consumer, you can take them, that means there is very limited option of tapping, and then since it is high voltage you can save on copper because it has to carry low current, okay, and this is and then you have only one wire, not the 4 wires which has to go in front of everybody's house. So, this is being thought of as an alternative nowadays for providing electricity. It is called a high voltage distribution system, okay, single wire. Now, what is the problem of this? No, power it will carry, the power you can have the wire, suppose it is 10 kilowatt, it will carry 10 kilowatt. The problem here is most of your domestic loads are okay, it can work on single phase, but agricultural loads are typically pumps, water pumps. So, that means the problem is to run a 3 phase motor using the single phase supply, is not it? Because this will be at 230 volts, 50 hertz, okay, 250 hertz, that will be okay for your house to run your fan, run your refrigerator, run your other domestic loads, but the same wire will have to, it will go to the farm here, okay, for water pumping, okay. Now, if it is a farm here, so then it has to run a pump, water pump, where it is most convenient to use 3 phase system, okay. So, this is where you have you have to understand a mechanism by which a 3 phase motor can operate with single phase supply, okay. Not because usually they may be 5 HP, 10 HP, etc. No? To build big machine single phase motors, you have main auxiliary winding, it is all a big problems, it is expensive, inefficient, making it difficult, etc. So, there has been work for quite a few times. In fact, the first PhD in the electrical department here was on this topic, okay, on this operation of 3-phase motor and single phase supply with the Professor CSJ was the supervisor. Okay. Now, next is I have told you these are the positive aspect of this study. Okay, now I will talk to the what I say negative motivation. Okay. What is happening is many of the states were very heavy like Punjab, Rajasthan and several of these states for example, in the the electricity board do not want to the people to use the pumps in certain hours because there is a shortage of power. Okay. So, what they do is the normal 3 lines are there, okay, and this fellow is using his pump. Okay. So, he is supplying water, okay, to his fields, okay, and suddenly after all this is giving you 3-phase power to these motors here, right. So, farmer is happy because he is having his enough water to the field, etc. But then the electricity board is not happy because electricity board does not have that much of power to supply to all the pumps at that point in time, because maybe at that time it is required for other domestic consumers, right, maybe in the evenings with heavy loads, because load patterns will be changing and certain time they do not want the pumps to operate. So, what they do is, okay, they disconnect. So, one line out, this is open, this is what they do. So, the consumer, that means it is single phase, that means motor will stop, but farmer is not happy, he is unhappy, he is angry on the other hand. Not only they steal power, but also they want to use power also, okay, sometimes, right. Is this in right vein, right, and so but he wants to have to run the motor now with single phase supply, okay. So, he only gets 415 volts say between these two terminals and here nothing is open, right. So, this is a sort of the farmer wants to be smart and beat the system, okay. So, very purpose of, so this is where what they have found out is a mechanism to run a 3-phase motor with single phase supply, okay. But the two systems there is one difference. See what I told earlier, this is at 230 volt 50 hertz, okay, and this one is at 415 volts 50 hertz. So, there is a difference. So, line to line voltage will be different than positive motivation, negative motivation, okay. Now, so what is the method that you can have? Typically, so a 3-phase motor can be operated with single phase system and we connect capacitors, okay, across the phase winding which acts as a phase converter, okay. Now, this is a connection, one connection, this is a delta connection. Delta connection is you have a normal delta connected motor, okay. Then you connect a voltage source single phase here, this is the current and these are the 3 phase voltages, okay, VSA, VSB, VSC, carrying current ISA, ISB, ISC, and it will also carry a current IC say, going to there is a capacitor connected and this will work. Okay. Many times what they will do is they will have also they can even have a start capacitor and a run capacitor. Okay. Right. Now, this operates at what voltage generally? If this connection, what will be the phase voltage? This will be 415 volts. That means a normal 3 phase delta connected motor. Okay. So, you had a delta connected motor with a normal rating of 415 volts and which was running at 3 phase supply. So, what you find is this is open, this has become open now, is not it? When this is open, what you do is just connect a capacitor here and run it, okay, with this. So, it will become a single phase supply across these supplies only, okay. And I had a very interesting experience when we went to buy some items in Bhagirath place. It is supposed to be a very large electrical market of Delhi. Okay. So, there was a farmer from Rajasthan who came and asked that shop person, you give me a bacha capacitor and bada capacitor, that is the word he used. So, what he meant was a starting capacitor and running capacitor, one is small, another is big. So, this is the rural terminology is, and that means he knows these circuits. Okay. This all meant for running his pump when the electricity board disconnects one supply. So, this has become a norm. Okay. Therefore, the very purpose of disconnection is being lost in a way. So, they have two capacitors, one call it the bacha capacitor and this bada capacitor, right, and they are quite smart and they have been able to use it. Okay. Yes. That we will come to know that. So, now you have to think, okay, if it is how do you operate it at 230 volts?
Excuse me sir, if the motor is running, if one wire blows off, then still the motor continues running with the 2 phases even?
Yeah, but he is it does not, but after all if it is running, if it disconnected it is all right, but you want continuously 24 hours you are not running, no. He goes to the he goes to the farm and tries to run his motor, it does not run and discovers that one line is disconnected, no voltage is coming in that line. So, then he does this trick, okay, right. So, we have to see when you can have a star or delta. Let us see if this is the connection, okay, then how do you analyze it? Now, our next question is, how do you analyze such motors? We have learned several techniques, symmetrical component theory, rotating field theory, we have done 2 phase, 3 phase, symmetrical, asymmetrical, everything is done. This is also a type of asymmetrical connection. Tell me how do you analyze? Okay. So, you can analyze through symmetrical components, is not it? A 3 phase machine is symmetrical. Okay. So, only thing you have connected a capacitor. So, already you know these symmetrical components V1, V2, V0 and we know the impedances, right, this is known to you. Okay. Then VSA, VSB, VSC and these are all these are the stator phase voltages. Okay. V0, V1, V2 are the sequence voltages, Z0, Z1, Z2 are the sequence impedances. Okay. I hope by now you are familiar with all these things. Okay. Now, in this connection your terminal constraint, what are terminal relations now? You have got the V here and I here, this is I capacitor, right. So, this is VSA, one terminal constraint V minus VSA is 0, is not it, this loop. So, V, this VSA is here, V minus VSA is 0, this is VSB and this is VSC. Another is VSC, because this is VSA, this will be VSB and this will be VSC. So, VSC, and what is the current here? If this is, just one second, we call this as ISA, this will be ISB and this will be ISC. What will be this current? That will be VSC minus this will be ISC minus ISB, is not it? If this is Vs, because this is VSC, because this is VSA, VSB and VSC. So, VSC, if you take a loop equation here, so VSC minus JXC into ISC minus ISB is 0. Okay. I have taken this loop equation, I have taken this loop equation. Say this is one equation 1 and let us say the equation 2 or whatever it is. Okay. Now, you have to use the symmetrical components. Okay. Of course, it is easy for me to say using symmetrical components equation 3 we get sequence voltage as this, right. You know, to get at this equations you must do considerable number of derivation. So, I want you to derive and submit tomorrow or next day. Note down this equation. Okay. I will entertain the first 10 assignments only.
What is y1 and y2?
Y1 is 1 over Z1 admittance and Y2 is 1 over Z2. These are the positive and negative sequence voltages now, which will be a function of the admittances and the capacitance XC. Okay. A you know is the operator. This will be V1 and V2, they will have a vector quantity. Okay. Right. As I told you, I will accept the first 10 assignments only, which I get it into my room. Okay. Is it okay? Let us see who will work on this, right. Okay, Y1, Y2 are the positive and negative sequence admittances, that Y1 is 1 over Z1 and Y2 is 1 over Z2. Have you noted down the equation, all of you? Please note down this equation, and you know the terminal constraint. I think basically a simple circuit, solving the circuit. Agreed? Okay. So, for a given XC, V1 and V2 can be calculated for any speed. So, it is a, because Y1, Y2 are functions of speed. So, V1, V2 will be function of speed. Okay. So, if X is this thing, X is known, Y1, Y2 are known, then V1, V2 will be decided. So, thus the sequence currents and forward and backward task can be calculated. The next, you know, your calculation is simple, because you know V1 and you know Z1 and you can find out I1, is not it, and you know V2 and you know Z2 and you can find out I2, and you know T1 will be, now this is a 3-phase machine again, now do not, you know, 3 times I1 square RF, RF is a positive as a real part of this, by omega s, and T2 will be 3 times 3 by omega s I2 square RB. Okay. you know that this is standard positive sequence equivalent circuit, negative sequence equivalent circuit, okay. It is IR square, you can also get it. So, net torque will be T1 minus T2. So, easy to solve. So, all you know, all you have to do in the methodology is for a given capacitance speed, you find out V1, V2 from those expressions and find this, okay. Yeah. So, for satisfactory operation of the motor, it is essential to choose Xc such that the effect of negative sequence voltage is considerably reduced. You want less V2, is not it, and more V1, and because you want the negative sequence will create noise and vibrations, because of the backward feeds it will create noise and vibration. So, you will always find any unbalanced motor will start jumping, it will tell I am uncomfortable, okay. So, it will start jumping and you know like a baby cries, the motor starts crying, making noise, right. So, you must make sure that it is put to rest, okay, properly, okay. And therefore, you have to see that you will define what is the unbalanced factor in such cases is the magnitude of V2 by V1. V2 is negative sequence voltage and V1 is positive sequence voltage. Therefore, this, so that factor will be, you can get a expression, because since you know V1 and V2, you can easily find out V2 by V1, is not it, it is magnitude, this is the magnitude, that is why we have to have magnitude of this. So, this is called an unbalanced factor. Is it okay? Is it okay? So, so there is an unbalanced factor because of this, and this unbalanced factor will be given by this expression, okay. I am giving you final expressions, but again you have to derive. This is the expression for the unbalanced factor, and where the constants are K1, K2 are given by this, okay. This is K1, this is K2, and that will be root 3 cos phi 1 sin phi 1, where phi 1 phi 2 are the impedance angles of Z1 Z2, Z1 Z2 are impedance angles, etc. Okay. Now, you want to have minimum unbalance, is not it? You want unbalance to minimum. So, you take for what will be the capacitor for which the unbalance is minimum. So, you derive you know d by dxc of u, and then what you will have is you get an expression in terms of xc, where these are the constants C1, C2, C3 given by this, and again I want you to derive these things. Okay. Note down these expressions. Okay, I will give it. Okay, this is definitely an important assignment for all of you should submit. Okay. Okay, you can submit, but those who submit early will get a more credit. Okay. And deadline is of course by Monday. Okay, before the next class I must have it. Okay. Right. Then so solving this equation, you have to, because you can get the capacitance at all speeds to give you minimum unbalance. Okay. Right. So, we observe that a continuously that means you require a unbalance will not be same at all speeds, capacitor required for unbalance minimum unbalance will be different for different speeds. Okay. So, you need a continuously varying capacitor from start to run, that means you can't go on changing the capacitor, no, you start a motor, you can't go on changing the capacitor as the speed builds up. Okay. So, normally they have normally they have a start capacitor and a run capacitor. Okay. And let me tell you typical variation of Xc for minimum unbalance. this variation of Xc for speed so this may be some per unit is typically for it may vary something like this, okay, say from 0 to 1 per unit. So, this is a typical variation of capacitance. This is Xc, what will be capacitance? So, capacitance may be something like this, is not it? Now, that means you require a high starting capacitor, maybe low running capacitor. So, you should know what is a bacha, what is a bada. Okay. This is for starting, this is for running. Okay. So, I think I have given you enough of course, some of the things are given in one of our papers published, okay. You can read the paper subsequently, but derivations are not given in the paper. So, you have to derive. Okay. So, I close it here today. Okay. Tomorrow next class we will take up the star connection. Okay.